Okay, in the last video, we looked at this notion of identifying the states, whether it was an equilibrium state, steady state heat transfer, or transient state heat transfer. And what is plotted here is showing the rate versus the time. And what we have in a lot of these pictures of steady state heat transfer is often not the rate versus time, but basically distance and temperature versus distance. And in these situations, the temperature is fixed at two different points, and the steady state heat transfer is how it's characterized is by these constant rates of temperature differentials. So one of the things we want to do now is just sort of say to ourselves, how do we navigate through a problem? And I wanted to show you how I do it. It might not be the best way, but it is the way that I have. There are actually probably lots of ways, and this is just one way. I really encourage you to develop your own. Okay, so for me, where it starts is essentially reading the problem. And after I read the problem, the first thing that I do is I sketch or model what I see in the problem. And this kind of requires, this step requires, so that requires me to do this very important step, which is to simplify. And I simplify by taking information from the problem. And that comes in the form of hints like, it may say something like, highly insulated. And what you could take from that simplifying assumption is essentially that Q is 0 in that material or in that direction. So they may say something like, I have a tube that is highly insulated. And so they're kind of trying to imply that there's no heat transfer in that direction. Or they may say something like there's insignificant airflow, or it's in a vacuum, or you can neglect radiation, these sorts of things. So you look for, inside the description, simplifying cues or clues in order to sketch and model what is happening. And then after I do that, the next step that I usually take is I label all known quantities. And once I have that picture, I can start to ask myself, okay, what's going on here? Are there, the question that I might come to is, are temperatures, are T's fixed? I realize this is barely legible, but what can I say? So are the temperatures fixed? If they are fixed, do I have one temperature fixed or two temperatures fixed? So let's say that the answer is yes. Yes, is it 1 or 2? So obviously, if I have 2 points fixed, we know that this simplifies to something very familiar to us. This is steady state. This is a steady state situation. And then we have to ask ourselves, well, we have steady state. Well, how many dimensions of heat flow? So we'll have to look at the geometry once we know the steady state. And this is going to be tricky because essentially there's only one of these cases that we can do. If, for example, the answer is there are 3 dimensions, then we need a computer. Hands down, there's nothing we can do. If, for example, there's only 1 dimension, we can do it this way, there's only 1 dimension, how many media? There's another question for us. And well, if there's just 1, this is our classic situation. Q is negative K dt dx, or delta T delta X. If there's more than 1, then we are in a situation we have a composite. I'm just drawing a composite heat flow here, and then essentially you're looking to simplify. Again, this is very important to simplify things. Look for the layers that may be highly conductive. So you're comparing K and H values. Maybe you're going to consider any negligible resistance in this case, and basically you'll use the situation where you have series resistors. And you treat this as a series resistor, and you can solve that this way. Okay, so that's the one-dimensional case that would be easy for us. 3D, we need a computer. 2D, we would need to ask ourselves, okay, let's say there's 2 dimensions. Is it something that we, that is familiar to us? For example, is there a source of heat involved? Something like, is there a source of heat? So is there a Q dot gen? That is there, like something radioactive that's giving off heat, or current running through something? If it's not, and it's just basically two-dimensional flow, we have to ask ourselves, is it one of the simplifying situations that we know? For example, so the answer is no. There's no heat generation. Do you have a cylinder? Is it a cylinder? That's basically in 2D flow. Then we know the solution. But if it's not a cylinder, we're kind of stuck. You're going to have to go back and go to the computer solution. If you don't have a cylinder, go to a computer. Is there heat being generated? If the answer is yes, once again, we want to know what is the direction. And in this case, we really have only two solutions that we can deal with. One is in a wall. It's either what is the direction? It's either planar, and we have the solution where you have a source of heat and the temperature profile. This is at the center, and this is the x direction, and the heat is being transferred out of the medium. There are some simplifying equations for that that are in your FE materials. If it is cylindrical, once again, we have a simplifying solution that your FE material, check the FE reference, that's another solution that we can take on right away. So here we have already a very messy and crazy decision tree. We read the problem, we make a sketch, we look for simplifying assumptions that we can add into that sketch, label all the known quantities. After that, then we begin to ask questions like, are temperatures fixed? If they are, then I know that I'm in a familiar one of the steady state situations. Oh, I should say that right here. Well, is one of the temperatures fixed, or are two of the temperatures fixed? This is meant to say that two of them are fixed. So in two fixed temperatures, I have steady state. Then I need to make decisions based on the geometry of the heat transfer. Is it three-dimensional? I need a computer. If it's one-dimensional, there are some straightforward solutions that I know I can apply, whether it's a single material or a composite material, treating it as series resistors. If it's two-dimensional, I have very limited options. I need to know, is there heat being generated in this two-dimensional steady state situation? There sort of must be, because otherwise you don't know where the heat's coming from. The steady state is sort of an artificial state and can only happen by an infinite supply and an infinite sink. So there must be something happening. If there isn't, well, I can go to the known solution in the two-dimensional heat transfer, which is a cylinder. If it's not a cylinder, I'm kind of stuck. I'm back to the computer solution. If it is, there's a heat being generated, then I need to know the geometry of it. If it's planar, again, in your FE reference material, there are some equations for a planar situation. If it's cylindrical, there's equations for that situation. So this all came out of the decision of whether or not the temperatures are fixed. Now, if they're not, then I have a transient situation. That is a little bit more complicated, so the answer is no. So how do we deal with transient heat transfer? And there's also, I see that there's, I forgot to kind of deal with this tree here. If there's one that's fixed and you don't really know the other one, you're going to have to make another decision. And probably the answer to this question is really which process is controlling the rate of heat transfer. And to do that, you'd evaluate the Biot number. And the Biot number is going to either tell you to turn to convection or turn to conduction. And let's see, it looks like there's no room on this page to deal with it. So once you evaluate the Biot number, let's kind of consider what that looks like. Let's go to the next page. This is the Biot number. And the Biot number is really a ratio of resistances. So essentially, the Biot number is equal to the resistance of convection under the resistance of conduction. And this is very confusing, because really it's 1 over HA, 1 over K, or L over K. This on top is the resistance of conduction. This is the resistance of convection. But you can see that it simplifies in a very confusing way. It simplifies to something like, oh, go away. Whoa. It simplifies to H on the top, HA over, HV over KA, or HL over K. I'm missing an A term here. Your textbook or the FE reference uses this form, but this is a very legitimate form as well, because the volume is equal to the area times the length. So in this case, now, once we know is the Biot, if the Biot number is much greater than 1, then what we know is conduction, our conduction dominates, or it's slower. And therefore, what you need to do is, to get this one, is to solve the heat diffusion equation, we haven't gone over this equation, but this equation is basically, it's a partial differential equation. The change in heat with the second derivative, here, d squared t dx squared is equal to 1 over alpha dt dt. If you've had diffusion, you might recognize this as essentially the diffusion equation, and instead of T, you replace this with C, concentration, and this value would be replaced with D. So this is actually dc dt. This is the same equation if you've had mass transfer. So if it's not that, if it's actually the Biot number is less than 1, so here's the case where it's bigger than 1, here's where it's less than 1, you're going to have the case where our convection dominates, or in other words, it is slower. And in that case, you are essentially going to set the heat Q rejected, not rejected, you're going to set the heat carried away by convection, or the rate of that, equal to the heat lost by the solid. And this will be, how does this show up, this heat lost by the solid? This shows up as a drop in temperature. So you end up setting this HA T minus T infinity. This is the heat that is carried away through convection, setting that equal to the heat that is lost by the solid, and that ends up being rho v Cp dt dt, the drop in, the change in internal energy that is reflected in the drop in temperature with time.